Welcome back, everybody. In this video, we'll be working on section 2.3. The title is Modeling with Linear Functions. And basically what that means is that we're going to solve some story problems involving linear functions. So there's a lot of variety among questions that you can see. So we just want to try to do a couple of examples in this section. We're going to start by giving a little general advice about how to approach these types of problems. So this part is taken from the textbook, so you probably will see that in your reading. I just wanted to go over a little bit of this. So of course, when you're working through the problem, you do need to read it. Math, a lot of times you do need to read through a problem more than once to make some sense of it, and that's totally okay. You need to think about what quantities change over the course of the problem. Based on that, we want to describe variables to represent the quantities. Often in algebra, we use x's and y's, but the further you progress, the more likely you are to see other variables like c for cost or t for time, w for width, and things like that. So you might want to use meaningful variable names. Okay, often a picture is helpful. Occasionally, putting up a coordinate system can be helpful. If your problem has any kind of geometric sort of attribute, like it's something about rectangles or triangles, then it's a good idea to make a picture. Okay, you do have to carefully read the problem, decide what's important, and that in and of itself is a really helpful skill, just to prioritize and decide what is important. Look for information that gives values for the variables or parts of the model, like the slope or initial value. Okay, you want to try to figure out what you're trying to find. Okay, often in math, the way that the problem is written, what you're trying to find is near the end of the actual text. So this is kind of unlike English, where when you read a paragraph in English, like the topic sentence they say is most important, and everything that supports it comes after. In math, a lot of times it's upside down, so that you have a nice long story, and then at the end it says, okay, find whatever. So keep your eye out for what is you're actually asked to produce. You may need to build a table or a formula for a function. You frequently will need to produce a formula for a function. Some problems can be answered using tables or maybe just producing a picture, but usually you're going to need to produce a formula that you'll need to evaluate. It's a good idea to check and make sure that your answer is reasonable, right? So that's one of the benefits actually of doing a story problem is being able to tell whether or not your answer is reasonable. For example, just as a little easy example, we haven't like studied any kind of trigonometry or anything yet, but let's say that I had a problem like this in a class I taught like a long time ago. We had like a 8-foot ladder. It was making an angle with the wall. It was leaning against the house, and it was making like a 67-degree angle, and it was an 8-foot ladder. And the question was just to determine how high up the wall the ladder was going to reach. And you don't need to know really any trigonometry or anything out of this to know that it's not going to reach 12 feet up the wall. So you think about that. Can you reach 12 feet up a wall with an 8-foot ladder? The answer is no. You could reach 8 feet up the wall if you nailed the ladder to the wall. You couldn't reach 12 feet up. So that kind of thinking, just checking for reasonableness to make sure that your answer is reasonable, is a valuable skill too. All right, so read through this advice, and also, of course, read through the section in our textbook that will help prepare you for the problems in this section. I think it'd be a good idea to go ahead and try some examples at this point. So let's do that. So here's our first one. This is from our textbook. It says a city's population has been growing linearly. Everything in this section is going to be linear, so you don't have to worry about that. In 2008, the population was 28,200. By 2012, the population was 36,800. Okay, so that's kind of the background information. We're going to assume the trend continues. If it didn't continue, then we would be stuck, basically. We wouldn't know what to do at this point. We're going to predict the population in 2014, and then we're going to identify the year in which the population will reach 54,000. So once we have this You'll notice that the question doesn't come right out and tell us to find the function that relates time and population. But in order to answer these questions, we're going to need that function. So for part A, we're going to turn a year into a population. And then in part B, we're going to turn a population, that 54,000, into a year. So basically what we need is a formula that relates the two, population and year. We're working on linear functions now, and so we know from our earlier work that to write down a linear function, what you need to know is either a point and a slope or 2 points on the graph for the function. So for this one, it doesn't say which variable should be our independent or x variable. So we could do either. It's probably customary to use time here. So I'm going to make x be the year. We could do t if you want, but I'm just going to use x as this is our first one. And then our y will be the population. That will be our f of x. So we have that in 2008, it was 28,200. And then 2012, it was 36,800. So here I'm using the actual values for the years. If you wanted to, you could set this up so that like 2008 was year 0 and 2012 was year 4, right? But just for clarity, I'm just using the actual year for this. All right, so we're setting this up so that our input is the year and our output is the population, right? And so we need the slope, right? So the slope will be the change in population divided by the change in time. So we're going to calculate. We'll have 36,800 minus 28,200. That's divided by 2012 minus 2008. Okay, so let's go ahead and get that worked out. All right, so I've gone through the calculations. We ended up with 8,600 over 4, which I've simplified to 2,150. And putting the units on there would be a good idea. Our population was in people, and then our time was in years. So this would be 2,150 people per year. Okay, that's our rate of change in population. So now that we have the slope, we have 2 points we can use. I would just use the one with the smaller numbers, but you could use either. So then our formula in general looks like y equals mx plus b. So we know that our slope is 2,150. We need to solve for b, so I'm going to substitute in our x value, which is time. And then that will give us the y value of 28,200. Okay, so then we need to solve for b. Okay, so that will give us our y-intercept. So let me figure that out for us. So that is negative 428,900. Okay, so that will be our y-intercept. So putting together the pieces, we have our f of x. That will be our population at time after year x. So that will be 2,150 x minus 428,900. All right, so there's our formula, and all of that was basically just to help us answer this first question, which is to predict the population in 2014. So let's go ahead and do that. So once we've done that, the rest of this should be pretty smooth sailing. So we want f of 2014. Here the numbers would have been smaller if I had chosen to make 0 for 2008 and then 4 for 2012, and then for 2014 that would need to be 6, right? But here I just thought it was clearer. So even though the numbers are larger. Okay, so then again, let's calculate. Okay, and that looks like 41,100. Okay, so now to do part B, instead of knowing the time, in part B, we know the population. So we want to work backward and figure out the year. So take a minute and think about how that's going to have to look. So for part B, we wanted to know the year in which the population was going to be 54,000. So what I did was set f of x equal to 54,000 and then solved. So 54,000 is 2,150x minus 4,289,000. I've added that 4 million and change to both sides, and then finally divided by 2,150, which gives us 2020 for the year in which the population will reach 54,000. So looking back, we read through the problem. We figured out that a linear model or linear function was going to be appropriate. Whenever we're writing down a linear function, we're going to need either 2 points or a point in the slope. We determined that we have 2 points. So then we calculated the slope. We substituted in the slope and 1 point to get the y-intercept. We assembled our pieces to get the whole equation or formula for our function, and then we answered a couple of questions, one of which we're basically given the x and calculate the y. The other one, we essentially were given the y and calculated the x.